Hello, and welcome to Lesson 11 of this Introduction to Differential Equations with Wolfram U. In this lesson, we will discuss second-order differential equations with constant coefficients that have complex roots to the characteristic equation. Let's take a look at an overview of this lesson and review the types of characteristic equations that we have already discussed. We saw in Lesson 9 that equations of this form, where the coefficients are all constants, can easily be solved through the use of the characteristic equation. In that lesson, we only considered differential equations where the associated characteristic equation had real, non-repeating roots. In this lesson, we will consider characteristic equations where complex roots are present and discuss the methods to solve such equations. We will see that the solutions of these equations can be written in exponential form where the imaginary unit is in the exponent. Let's begin our discussion with a linear homogeneous second-order differential equation with constant coefficients. Like we did before, assume the solution is of the form e to the lambda x, and substitute that form into the differential equation. Doing so leaves us with the characteristic equation produced here. When we considered the characteristic equations associated with differential equations in prior lessons, we only considered polynomials that had real roots that were distinct. In this lesson, we will generalize this to include complex roots. When the roots are complex, the two roots denoted by lambda 1 and lambda 2 are of the form given here. Each value for lambda will correspond to a solution to the differential equation of the form e to the lambda 1x and e to the lambda 2x. Looking at the form of the solutions, we can see that we're going to get a real part, the e to the rx part, and an imaginary part, the e to the I gamma x part. We will discuss shortly how to interpret a function where the imaginary unit appears in the exponential using Euler's formula. First, let's verify that the functions y1 and y2 here are indeed solutions to the differential equation. Let's verify that e to the lambda x does solve the differential equation when lambda is a complex valued root to the characteristic equation. To do this, substitute e to the lambda x into the differential equation and use one of the complex roots for lambda. Here we will use lambda equals r plus I gamma as the root. To show that the equation is satisfied, we need to simplify it while assuming that r plus I gamma is a root to the characteristic equation. We are doing this here by using assuming. The assumption is saying that a times lambda squared plus b times lambda plus c does in fact equal 0 when lambda is equal to r plus I gamma. Now that we have the assumption defined, simplify the equation using these assumptions. Under the assumption that r plus I gamma is a root to the characteristic equation, we can see that e to the lambda x does solve the differential equation. The same can be shown to be true for e to the r minus I gamma x by replacing this form for the solution into the differential equation. Like before, simplify the result while assuming that r minus I gamma is a root to the characteristic equation. As can be seen, e to the r minus I gamma x is also a solution to the differential equation. This demonstrates that e to the r plus I gamma and e to the r minus I gamma are both solutions to the differential equation. Let's now take a moment to consider what is meant by an expression that has the imaginary unit in the exponent. To understand an expression like e to the r plus I gamma x, it is necessary to examine the Taylor series expansion associated with the exponential function e to the x. Remember that the Taylor series for e to the x can be represented as an infinite series where each term in the series has an increasing power of x in the numerator, while the denominator grows as a factorial. It is easy to demonstrate this relation in the Wolfram language. Replacing x with I times x gives the Taylor series for e to the ix. Let's expand out the series and take a look at the first few terms. It may not be immediately obvious, but if we group some of these terms together, we will find the Taylor series for some functions that should be very familiar. Consider again the sum from the previous slide. If we look at the first term, the third term, the fifth term, the seventh, and so on, we will see that the sum is exactly the sum for cosine of x. Therefore, we can group these terms together and call them cosine of x. In a similar way, if we look at the second term, the fourth term, the sixth term, and so on, we will see that this is the series for I times sine of x. Therefore, we can group those terms together and call them I times sine of x. More specifically, the Taylor series for e to the ix can be expressed by the Taylor series for cosine of x plus I times sine of x. We can again show this equality very easily in the Wolfram language. Therefore, we can conclude that e to the ix is equal to cosine of x plus I times sine of x. We have shown on the previous slide that e to the ix is equal to cosine of x plus I sine of x. We can use this result to calculate the value of any complex exponential. For example, e to the r plus I gamma x can be broken down into a product of e to the rx and e to the I gamma x. The e to the rx term can be calculated like any exponential, while the e to the I gamma x term can be broken down into sines and cosines using Euler's formula. As a specific example, consider e to the 1 plus 5ix at x equals 1. The e to the 1 times x part can be pulled out front, while the e to the 5ix term can be written in terms of sines and cosines using Euler's formula. If we want to evaluate the expression at x equals 1, simply replace x with 1 in this equation. This can easily be calculated in the Wolfram language. It is important to note a very interesting mathematical fact, that when e to the ix is evaluated at x equals pi, the result is equal to minus 1. This demonstrates Euler's identity that e to the I pi equals minus 1. Let's solve a linear second-order homogeneous differential equation with constant coefficients in the case where the characteristic equation is complex roots. We can identify the characteristic equation as lambda squared plus lambda plus 1 equals 0 by looking at the coefficients of the differential equation. Once we have identified the characteristic equation, find the solutions with solve and assign the results to the variables lambda 1 and lambda 2. The solutions to the characteristic equation are of the form r plus or minus I gamma, with r being minus 1/2, and gamma being the square root of 3 over 2. Now that we have the lambda values which solve the characteristic equation, we can write the general solution as a linear combination of the two solutions, e to the lambda 1x and e to the lambda 2x. With the general solution found, let's solve the initial value problem by finding constants that satisfy the initial conditions. Let's use the initial conditions to find the constants which solves the initial value problem. First, use the condition that the solution equals 1 at x equals 0 to set up one equation involving the constants. In a similar way, use the condition that the first derivative equals 5 at x equals 0 to set up a second equation. Now we have two algebraic equations involving the two constants, so we can solve the set of equations for those two constants. The solution to the initial value problem is then obtained by replacing the constants we just found into the general solution. This function here is thus the solution to the initial value problem. On the previous slide, we found this to be the solution to the initial value problem. First, let's verify that the solution we found satisfies the differential equation by substituting the solution back into the differential equation. It can be seen that the solution does indeed satisfy the equation. Now let's confirm that the solution satisfies the initial conditions at x equals 0. We can see that the solution does satisfy the condition that it equals 1 at x equals 0, and that the first derivative at x equals 0 is 5. Now let's compare the solution we found with the solution returned by dsolve value. The solution we found and the solution from dsolve value seem to differ. However, this is simply due to using the exponential form rather than the sine and cosine form as in dsolve value. While the two solutions appear to differ, we will show that they are actually equivalent. We will now discuss how to arrive at the dsolve value form by examining the concept of fundamental solutions. In the previous example, we found these two functions, y1 and y2, to be solutions to the second-order differential equation we were considering, which had constant coefficients and a characteristic equation with imaginary roots. We will show here that even though these are the two solutions, we can represent the fundamental solutions to the differential equation in many forms. This will explain why dsolve value gave a different form for the result on the previous slide. Begin by using Euler's formula to break the solutions down into trigonometric forms, sines and cosines. The important point to note is that because these two functions satisfy the differential equation, any linear combination of these functions will also satisfy the differential equation. This is useful because we can choose a convenient linear combination that puts the fundamental solutions into a simpler form. For example, if we add y1 and y2, the imaginary parts will cancel, and if we subtract y1 and y2, the real parts will cancel. Using this linear combination puts the fundamental solutions into a very simple form, since they are represented by just cosines and sines times an exponential and some scalar constant that we can ignore for the moment when discussing fundamental solutions. Now let's consider the Wronskian determinant of these two functions to determine if they do indeed form a fundamental solution set. Let's check to see if the functions y1 and y2 we obtained on the previous slide form a fundamental solution set. First, define the two functions in the Wolfram language. Now, with the functions defined, calculate the Wronskian. We can see that the Wronskian is non-zero for all values of x. Therefore, by the Wronskian determinant theorem, we can conclude that these functions do form a fundamental solution set to the differential equation. Introducing the arbitrary constants, we can write the general solution in the same form given by dsolve value. What remains is to find the constants C1 and C2 so that the general solution satisfies the initial condition. In order to find the constants, use the initial conditions like we did before to set up a system of two algebraic equations for the two constants. With the system of equations established, we can easily solve for the constants. Replace these values for C1 and C2 into the general solution to find the solution to the initial value problem. Now compare this result with the result from dsolve value. We can see that the two solutions are identical now that we are using a fundamental solution set based on sines and cosines. As we have seen in the previous slides, if the roots of the characteristic equation are r plus or minus I gamma, then the general solution to the differential equation can be written in this form involving real exponentials and sines and cosines. Using this information, let's solve this second-order homogeneous differential equation with constant coefficients. First, identify the characteristic equation from the coefficients of the differential equation, then solve the characteristic equation for lambda. We can identify the r and gamma parts of the roots to be -1 and square root of 3 respectively. Using these values, we can write the general solution to this differential equation as this. Here we are using -1 in the exponent, square root of 3 in the cosine and sine terms, and including the arbitrary constants c1 and c2. Now let's solve the initial value problem. Like before, use the general solution to set up a system of algebraic equations involving the constants. With the system of equations defined, solve for the two constants. Now that we have the constants found, we can write the solution to the initial value problem by replacing the constants into the general solution. Finally, compare with d-sol value to verify the solution. We can see that the two solutions are identical when we begin with the fundamental solution set involving cosines and sines. In previous lessons, we discussed homogeneous second-order differential equations with constant coefficients of this form here. We have discussed how these types of equations can be solved quite easily using the characteristic equation. In this lesson, we examined the case where the roots of the characteristic equation were complex and of the form r plus or minus I gamma. When this is the case, the general solution can be written in this form, where r is the real part of the complex root, and gamma is the absolute value of the imaginary part of the root. The coefficients, c1 and c2, are then determined by initial or boundary conditions.